Functions and their representations. The first thing we'll want to talk about with functions is function notation. The notation y equals f of x is called function notation. The input is x and the output is y. The name of the function is f. So in this notation it looks like it's f times x, but it's not. In this context it's simply function notation saying that the function f of some input x gives us some output. And like this says quite literally, f of x is y. So instead of writing equations like y equals 3x plus 2, we'll write our equations as f of x equals 3x plus 2. Now a function works a lot like a function machine. Here we have a function called g of x, and it is g of x equals x plus 5. We put in some input x. Here we're putting in 4. So here you see the input 4. This function adds 5 to that input, and the output is 9. So there are a lot of things in everyday life that act a lot like a function. Think of things like a soda machine. If you put quarters into a soda machine, that would be like your input. And based on which button you press on the machine, out comes a Sprite or a Mountain Dew or a root beer or something like that. So you're putting an input in, it does something to the money there, and out comes a soda. Here let's evaluate f of x at the given values of x. F of x equals 3, and we have the values of x equals -8 and x equals 7/3. So first what we do is we write f of -8. So we're replacing the x in the function notation with the x value -8 equals 3. Here it's a constant function. It doesn't matter what we put in. 3 is always going to come out. So for f of 7/3, when we put in a 7/3, out comes 3. So let's try our next function, f of x equals x squared plus 5. I have a f of, they want us to put in a -1/2. And this function takes the input, squares it, and adds 5 to it. So when we simplify this function, we get a -1/2 squared is a +1/4 plus 5, which gives us 21/4. And let's try f of 6 now. F of 6 would be 6 squared plus 5, so 36 plus 5, which is 41. A function is a set of ordered pairs x, y, where each x value corresponds to exactly one y value. In short, every x has exactly one y. If you're asked this definition on a test or a final, it's just fine to say that a function is a set of ordered pairs where every x has exactly one y. So here we have a couple of things that might describe a function. Let's look at these things and decide whether they are a function or not. The first one is calculating the square of a number x. So does every number x have exactly one square? Yes, it does. 5 will only have a square of 25. 3 will only have a square of 9. Everybody who squares a number will get the same number that everybody else gets when they square the same number. So yes, this does describe a function. Let's look at this one, listing the students who passed a given math exam X. So does every math exam, does this one math exam have exactly one student who passed? Hopefully not. So we're going to say no, this does not describe a function. Here are some examples of functions that are mathematical. So this function is the function f of x, and it equals 2x minus 7. In other words, it's going to take the input and double it and subtract 7. So the name of the function, here let's take an input of 3. The output is going to be 2 times 3 minus 7. When we simplify that, we get negative 1. So you see here that the x has been replaced with 3, and the thing that comes out is the y. Remember, f of x equals y. So f of x equals y. So this is the x, this is the y. We can see here in this function notation, we actually have the coordinate 3, negative 1. Over here, we have a function g of x equals x squared plus 5. The name of the function is g. Let's put the input of 3 in this one as well. And this function squares the input and adds 5, so we're going to square 3 and add 5. When we simplify that, we get 14. So the x was 3, and g of x, or the y, equals 14. So we have an x of 3, a y of 14. It corresponds to the point 3, 14. For the following, let's write a formula for the function described and evaluate the function for input 10 and then interpret the result. So function m computes the number of miles in x feet. So they tell us that they want the function to be called m, and the variable that they want us to use inside is the x feet. They could have said r feet or t feet, but here they said x feet. So we'll call this function m of x. And this is going to equal the number of miles in x feet. Well, do you know how many feet are in a mile? There are 5,280 feet in 1 mile. So let's come up with a formula. If I had, let's say if I had 1 foot, x number of feet, so x is 1. If I had 1 foot, how many miles is that? It's 1 over 5,280. If I had 2 feet, that would be 2 over 5,280. Of course, you simplify and so on. So my formula looks to be x over 5,280. Now let's go ahead and evaluate that function for 10. So I'll have m of 10. That's 10 over 5,280. And if you like, you can grab your calculator and put this in on the calculator. 10 divided by 5,280. And let's go ahead and put this in decimal form. Let's say we go to 5 decimal places. We have 0.00189. So 0.00189. We'll replace that equals sign with an approximate symbol. So this is approximately 0.00189 miles. So if we have gone 10 feet, then we've only gone 0.00189 miles. And that is our interpretation of the result. We don't want to just say that m of 10 equals 0.00189. And we don't want to just say that if we have an input of 10, then the output is 0.00189. You want to describe this in everyday terms that somebody who doesn't understand functions would be able to understand. So we would say if we have a distance of 10 feet, we have a distance of about 0.00189 miles. So you've mentioned both the input and the output, but in the context of the problem where x is the feet and the output is in miles. Now let's look at this one. This function is function A, and it computes the square feet in X acres. There are 43,560 square feet in 1 acre. So if I have this function A, and they're having us use X acres, so X will be our input value. And let's say that we had 1 acre. If we have 1 acre, then how many square feet do we have? Of course, 43,560. If we have 2 acres, then we have double that. So our formula is simply going to be 43,560 times our input X. So however many acres we have, we multiply it by 43,560 to get the number of square feet. So let's see, let's go ahead and evaluate this for 10. So A of 10 equals 43,560 times 10. So we get 435,600. And of course, we know that that is in square feet. So what does that mean? It means if we have 10 acres, then we have 435,600 square feet. Again, we mention the X in the equation and the Y, the output, but we don't just talk about them as inputs and outputs. We talk about them in regular everyday terms. Here, let's make a connection with our function notation and a graph. If we have an f of a equals b, then we have the point AB that lies on the graph of f. Conversely, if we have a point AB lying on the graph, then f of a equals b. So we can graph these points by finding a and f of a. So let's use the graph of f to evaluate the given expressions here. If I have f of 0 or f of 2, what are they talking about here? Well, f of 0 means, well, they've replaced x with 0. So they're saying, oh, well, this is the point on that graph where x equals 0. So that's the point 0, 3, isn't it? So if we have the point 0, 3, then f of 0 equals 3. Now let's find f of 2. F of 2 would be over here. So this is where x is 2. It's the point 2, negative 1. So that means that f of 2 is negative 1. On the next one, let's find f of negative 2 and f of 1. So we're looking here at f of negative 2. We're finding x of negative 2. We happen to be right on the graph, right there. So that's the point negative 2, 0. So f of negative 2 must equal 0. Now f of 1, we make x 1, and f of 1 is up here. So on the function we have 1, 2, so f of 1 equals 2. Now let's sketch a graph of f here, and you'll notice it's f of x equals 1/2 x minus 2. That's the same as y equals 1/2 x minus 2. So really, it's just the graph of a line. So we can look at this as y equals mx plus b form. This would be our slope. And this is our b, our y-intercept. So we have this y-intercept of negative 2. And to get to the next point, we use our slope of a rise 1 and run positive 2. So rise 1, run positive 2. We can do that as many times as we like to make it clear where our line is going. And then we just need to draw our line with arrows through it at the ends to show that it keeps going on both of those directions forever. So that's a sketch of f. Let's say we want to sketch this graph. That's something that you may not be familiar with, so let's say that we make a t-table of values. Now a lot of times it's good to make a t-table of values that start with some negative numbers, 0, and go through some positive numbers to get a nice array of numbers to try in that function, especially if you don't know what that function looks like at all. So if we try this and I put in a -3, -3 plus 1 is -2, and the square root of -2 is not going to be real, so apparently we can't use that value. If we put in a -2, -2 plus 1 is -1, and then we're taking the square root of a negative number again. So we can't use -2. Let's try -1. -1 plus 1 is 0. And the square root of 0 is fine. It's just 0. If we put in 0, 0 plus 1 is 1, and the square root of 1 is 1. We put in a 1, 1 plus 1 is 2, and the square root of 2, if you'd like to, you can put this in on your calculator. Square root is underneath that x squared button, so we have to use that second button to get to the square root of 2, and hit enter. We get about 1.4. We can just round this to 1 decimal place because 1 decimal place is about as accurate as we can graph on a scale that is this small. So we'll go about 1.4. Okay, approximately 1.4. If we put in a 2, 2 plus 1 is 3, and so then we're taking the square root of 3, and we get about 1.7. And we put in a 3, 3 plus 1 is 4, and the square root of 4 is, of course, 2. Let's go ahead and graph those points. So we have a -1, 0. We have a 0, 1. We have 1, 1.4, 2, 1.7, and 3, 2. So you'll notice this is not a straight line. It's curving a little bit there. So, what's going on? Maybe if we pick another number further out. We knew we didn't have any luck going this way, but let's say that we pick a number out here. I'm going to pick an 8 just because if I put 8 in there, 8 plus 1 is 9, square root of 9 is 3. We get a whole number out. So let's see, if I go 8, then I get 3. So we see that this is going up pretty fast, and then all of a sudden it's leveling out really slow. So it's doing this type of thing. Now I could keep going if I wanted to keep picking numbers this way, couldn't I? So what happens is that this levels out. It keeps going up, but very slowly. And on this side, we know that we didn't have any luck with numbers to the left of -1, so we have to stop right there. All of your square root graphs are going to have that general shape. Let's use the table to evaluate the given expressions here. So we have f of 0 and f of 2. All we're doing is saying that, well, instead of saying f of x, they're telling us that x is 0. So when x is 0, what is f of x? 5.5. So when x is 0, f of x is 5.5. We have the point 0, 5.5. How about f of 2? If I have f of 2, then it's telling me the x is 2, and the f of x when x is 2 is 3.7. I have the point 2, 3.7. You can see that right in the table. So you've seen we have various ways to represent our functions. They're not always just formulas. We have a numerical representation, which is a table of values. We have a symbolic representation, is what we usually deal with, the formulas. F of x equals 3x plus 2. A graphical representation, we've been looking at a lot of graphs. A schematic representation is a diagram. We'll see those in a little bit here. And a verbal representation is a word description, such as computing the square of a number x. That would be a verbal representation of a function. So here let's use the diagram to evaluate f of 1990, and then we'll interpret the answer. Function f computes the average cost of tuition at public colleges and universities during academic year x. So here we have a schematic diagram of a function. The first set of numbers in that set is called the set of inputs, and they're getting sent by this function f, getting sent into a second set, which are your outputs. So if we're evaluating f of 1990, we want to look at an input of 1990, f of 1990 equals, that's getting sent to 1,809. So here we have of course, our function notation that shows a point, the input and the output, the x and the y. But let's go ahead and interpret the answer. Remember, when we interpret the answer, we want to describe this in language that people who don't know math would understand. So something that maybe you would hear on a newscast. We wouldn't say, well, for an input of 1990, we get an output of 1809. That wouldn't make sense to most people. So what we want to say is, in the year 1990, the average cost of tuition at the public college and universities was $1,809. Okay, so we've mentioned the x and the y, but in the context of the problem where 1990, our input, is a year, and 1809 is our output, but it's in dollars. Let's give a verbal representation for f of x here. F of x is a function x minus 1/2, so it's taking all of our inputs and subtracting half every time. So that is the verbal representation. Subtract 1/2 from the input. So any input gets 1/2 subtracted from it. Cost of driving. In 2010, the average cost of driving a new car in the United States was about 50 cents per mile. Symbolically, graphically, and numerically represent a function f that computes the cost in dollars of driving x miles. For the numerical representation, or a table, let x equal 10, 20, 30, all the way up to 70. So increments of 10 up to 70. So our first step is to find a symbolic representation of this function. So they want us to use f as the name of the function. So we have f of, and they want us to use x as our input. So f of x computes the cost of dollars. Let's see, the cost of driving a new car is about 50 cents per mile. So if we would drive 1 mile, it costs 50 cents. If we drive 2 miles, then it costs about $1. 3 miles, $1.50. So what we're doing is multiplying each mile by 0.5. So 0.5x, or you could also write 1/2 x. So that is our symbolic representation of the function. And let's represent this graphically. So here we have a graphing grid, and along the x-axis is going to be our x miles. So x is in miles, and the y-axis is going to be our cents per mile, or the cost. So let's put that, y is the cost. Now helps if we write this as a fraction when we go to graph this. So if we write this rather as f of x equals 1/2 x, then we can recognize that this is the slope and the y-intercept is 0. So we'd have this point at the origin. This is just the first quadrant, the upper right-hand quadrant. So we have the point 0, 0, and then to get to the next point we go up 1, right 2 for the slope of 1 over 2. Up 1 over 2. Up 1 over 2, and so on. And then we connect that, of course, with our line. And let's make sure I've got that on there correctly, and put an arrow. It doesn't make sense to put an arrow here because in practicality we can't drive negative miles. Alright, so this is our graphic representation of the function. And then let's represent this numerically. Now numerically is a table. So numerically we make a table, and they've told us the values to put in the table: 10, 20, 30, 40, 50, 60, and 70 in that table. When I put a 10 in here, 1/2 times 10 is 5. So if you drive 10 miles, it costs you $5. 20, if I go 20 right there, 0.5 times 20 is a 10. In other words, all of our y's are going to be half of what those were. So 5, 10, 15, 20, 25, 30, 35. Right, you can see that a numeric representation is not a complete representation of that function, because we could drive maybe 12.8 miles, and that's not on the table. So you have to understand that the numeric representation of a function is not complete. It's going to be for specific values that you're told to put in, or something that makes sense in a presentation. Here we have a definition for domain and range. Now the domain of a function is the set of all valid inputs. In other words, the domain is the set of all x values. So the set of our inputs is the same as the domain. In science classes, they usually will call this an independent variable. Now you notice that I've underscored the word valid. So not all inputs are going to be valid for a function. Often it's going to be all real numbers, or in interval notation, negative infinity to infinity. However, there are times when domain is restricted because of the function. Functions with x in the denominator. Remember we did that in the last chapter, where we have a function, a rational function, where x is in the denominator, and you can't allow x to be certain values because it causes that rational expression to be undefined. It causes division by 0. We also have restrictions when we have square roots. And we saw that in this example, where we have a table, but goodness, some of those values didn't even work. So apparently -3 and -2 are not valid inputs. They're not going to be numbers that are part of the domain for this function. So part of our task is going to be figuring out what the domain of a function is. Now the range of a function is the set of all the outputs. In other words, the range is the set of all the y values. So outputs is the same as range, and they would call that, maybe in a science class, the dependent variable. The output of a function depends on the independent variable, the thing that you put in the function in the first place. So here, let's write each of these functions as a set of ordered pairs and give the domain and range of f. So we write this like this: f equals, and then we open up a curly brace, And we'll list the ordered pairs in that function and then close it with a curly brace, showing that we're finished describing that set. So the first set of ordered pairs, we have f of 1 equals 3, so we know we have the ordered pair 1, 3. The next one we have f of 2 equals negative 4, so we have the ordered pair 2, negative 4. And the next one we have f of 3 equals 0, so that means we have the point 3, 0. And close your curly brace. So this is writing the function as a set of ordered pairs. This is called roster notation, where you have curly braces, you list the elements, and separate the elements by a comma. So let's give the domain and the range of f. Domain and range, all we do is put a D colon and an R colon. And the domain will list in roster notation as well. Domain, remember, is the set of all the inputs, or the set of all x's. So we have 1, 2, and 3. We have 1, 2, 3. Like that. Range, we start the same way, curly brace, and we have 3, negative 4, 0. But let's go ahead and put those in numerical order. We have negative 4, 0, 3. It just helps the reader to have those numbers in order from left to right. Now we have this set of inputs and outputs in this function that are all just variables. So we can still do this. We have f equals, open a curly brace, and we have the point, well, f of a equals b, so we have the point a, b. We have the point c, d. We have the point d, b. Now we're going to find the domain and the range. So the domain is the set of all the x's, the first values in those ordered pairs, or the input. So we have A, C, and D. So we list those, separated by commas, close the curly brace, and range is the B, D, B. Now there's no need for us to list B twice. We can just list it once and put our D, and of course those are in alphabetical order. So we're finished with listing the range points. Let's find the domain of these functions. Now they're not graphed for us, and we don't need to graph them. We can find out the domain just by looking at the equation and knowing something about the nature of those equations. Now we said earlier the only time we'll have restrictions on domain is if we have a denominator with x in the denominator, or if we have a square root where x is under that square root. If it doesn't have those two things, then there are no restrictions on what x can be. There are no restrictions on the domain. So if it doesn't have those two things, then your domain will be all real numbers, or negative infinity to infinity in interval notation. Now later on in your math career, you will have some other types of functions that have restrictions on domain, and that will be when you get into logarithms. But for the rest of this class, we'll only have those two cases of restrictions on domain. For this first problem, f of x equals 10x, the domain is going to be quite simple, just negative infinity to infinity. We don't have a square root, and we don't have a denominator, so there's no chance that there are going to be any values on this that are disallowed for that function. We could put any x value in, and we'll always have something defined come out. When we have a function like this, still the domain is negative infinity to infinity. We don't have a denominator with x in it. We don't have an x under a square root, so the default domain is all real numbers. When I'm looking at a function like this, I do have a denominator with x in the denominator. So the restriction over here is that the denominator cannot equal 0. If that denominator equals 0, then we have division by 0, which is going to be undefined for us. So if we solve this inequality, we get x cannot equal a positive 5. So this is your domain in inequality notation. Let's think about what that looks like if we would graph it. Here's 5, and it's not including 5, but it's including everything else. So if we put this into interval notation, we would have negative infinity to 5, put a parenthesis so it shows that you're not including 5, union, parenthesis, 5, comma, infinity. Alright, for this next one, it looks a little different. We have an absolute value, but again, it's not a square root, and we don't have a denominator with x in the denominator, so the domain just defaults to all real numbers, negative infinity to infinity. Here we do have a restriction because we have a square root and x is under that square root. So what is the restriction for these types of functions? If you recall on this problem, the reason we couldn't use those values is when we put them in, it caused the radicand, the stuff that's underneath that square root, caused the radicand to be negative. So we cannot take square root of negatives. That's the problem here. If I put in a negative 1, it made it 0, but it's okay. I can take the square root of 0. So when I'm looking at this, I say, well, that radicand, if I want to be able to use this function, the radicand must not be negative, or in other words, has to be greater than equal to 0. If it's greater than 0, then the radicand is positive, and I can take square roots of positive numbers. If it's equal to 0, then that's fine. I can take square roots of 0. So let's go ahead and write this. The radicand literally is 2 minus x. So 2 minus x greater than equal to 0. If we can solve this inequality, then we have the answer to our domain question. I'm going to subtract 2 from both sides. And when I divide by negative 1, remember I have to flip that inequality. And so I get an x of less than equal to 2. If you'd like to see that graphed, here we can put 2. And x is less than equal to, so we're going to go shade to the left and a square bracket right there. So we have the domain as negative infinity to 2 with a square bracket, and we're reading that from left to right when we put that into interval notation. Let's determine here whether the diagram represents a function. If it does, then we'll also list the domain and the range. So here we have this f here, function. Let's see, is it really a function? Does every x go to exactly 1y? Yeah, 1 goes to exactly one number, 2 goes to exactly one number, 3 goes to exactly one number, and 4 goes to exactly one number. So yes, this is a function. And let's find the domain and the range for it. The domain, remember, is the set of all of the x's. So 1, 2, 3, 4. Putting this in roster notation. And the range is the set of all the outputs. 5, 6, 7. Also in roster notation. Is this diagram representing a function? Here, 1 is going to 4 and to 6. So this is an x that has more than one y. So this is not a function. Since it's not a function, we're not going to find the domain and range on it. For this one, is this a function? This x goes to exactly 1y. This x goes to exactly 1y. And this x goes to exactly 1y. So this is a function. It follows our definition of every x having exactly 1y. Let's find the domain. The domain is 1, 2, 3. And our range is one number 8. We still put it in the roster notation. Now we have something called the vertical line test that we use when we have graphs. If every vertical line intersects a graph at no more than 1 point, then the graph represents a function. So let's try this vertical line test on these. Let's determine whether the graph represents a function. If it does, then identify the domain and the range. Let me draw here a vertical line for you. Just take that line and draw it through your graph. Take your pencil and roll it across your graph. Does the line ever touch more than 1 point at a time? Doesn't ever there. So this passes your vertical line test. And does this pass the vertical line test? No. I mean, there's several places along here where we're hitting more than 1 point. So let's find the domain and the range for this one. The domain is, well, this is a line. It's going this way and this way forever. It's going to be covering all of our x's. So domain is from negative infinity to infinity. And the range, of course, this goes down forever and this goes up forever. So all of our y's are covered. So we have a range of negative infinity to infinity as well. Now I know that this does not represent a function, so we're not going to find the domain and range, but let's look at why the vertical line test actually works here. If you look here, we have touching at those points. That vertical line going through gives us 2 points. Those points are, well, let's say that they're probably 3, 2 and 3, negative 2. So you can see here we have one x, a 3, that has 2 different y's, 2 and negative 2. So that's the reason that that does not pass the vertical line test, and so that tells you why it's not a function. Let's see, would a vertical line test pass here? Yes. This is going to pass the vertical line test, so let's find the domain and the range. Now, when you're finding the domain, it's also helpful to roll your pencil across. If we rolled our pencil across with let's use a vertical line here, then let's see, what is the first x we come to? The first x we come to is a negative 4, and it keeps going. It's touching all these x's until we get here, which is a positive 4. So we have this domain of negative 4 to positive 4. And of course, those points are included. Now they don't have to be big bulbous dots for those to be included. Here they were kind of generous and let us have those nice bulbous dots to show that they are included points. But these are also all included points, and they're not bulbous dots. They're just part of the graph. Now if they do have an open point, you know for sure it's not included. So we have here from negative 4 to 4 on the x, and then if we wanted to do the same thing on our range, then we would draw a horizontal line up. So the first y value that we have is a 0, and it goes all the way up. We always have a graph until y is 4. So we'll have this range of 0 to 4, and of course 0 is an included point. It's a solid point right there, and 4, those are solid points. Now this is not going to pass the vertical line test. You can see if we draw a vertical line through there, it's going to hit more than one spot. So this is not a function. Doesn't pass the vertical line test. If you're ever asked why a graph is not a function, you can just say it doesn't pass the vertical line test. Is this going to be a graph that passes the vertical line test? We pass the vertical line through here. It sure does. So we have a domain here of, let's see, negative infinity to infinity, because this goes forever. All of our x's are covered. And the range is going to be just 3. 3 is the only y that comes out of this function. So what we do is we have to use roster notation. It's not an interval of points. It's just a single value. Now, does this pass the vertical line tests? It's a funny looking graph, but it still passes the vertical line test, so it is a function. Let's go ahead and find the domain and range. The domain goes from -4. We're covered until we get to +4. So -4 to 4, square brackets on those. And the range goes from -4 to +4. So -4 to +4 on the range as well. Is this going to pass the vertical line test? We can see right here it doesn't pass the vertical line test. We have, if we draw a vertical line through there, we have 2 points that vertical line is passing through. In other words, this is the point -2, -1. This is the point -2, 2. So we have an x of -2 going to 2 different y values. So this is not a function. Now, is this graph a function? Passes the vertical line test, so yeah, it's a function. Let's go ahead and find the domain and range for this one. Now, the domain isn't from -2 to 2. It doesn't include all the values between here and here, and between here and here, and between here and here. So we're not going to use interval notation. We're going to use roster notation where we simply list the values that are covered. So we have a -2, -1, 1, and 2. So -2, comma, -1, comma, 1, comma, 2. And the range is going to be -2, -1, and 1. Again, in roster notation, we only have 3 values where we have y's. Okay, so it's only -2, -1, and 1, not everything from -2 to 1. So we don't use the interval notation. Now, looking at these 2 different representations of some kind of a relationship between numbers, let's determine whether they are functions. For this one, we're looking at all the points, and it looks that every x is going to exactly 1 y. We never have a repeat of an x value, so there's no chance that the same x could go to 2 different y's. So yes, this is a function, and the reason is that every x has exactly 1 y. The reason is your definition of the function. If we're giving s by this table, then we have 5, 2, 10, 1, and 5, 0. Again, this is not going to be a function because we have 5 going to 2 different values. So this is not a function. And think about if you did have these points graphed, you'd have a vertical line going through 5, 2 and through 5, 0. It wouldn't pass the vertical line test. So not a function because we have an x that has more than 1 y. So that covers this section. Go ahead and try your homework. Be sure and let me know if you have questions.